In this example, we are being asked to compute several ratio values given certain other values related to a phase diagram. Now, one thing I want you to notice is this is example 3.1 in the text, okay? So in the textbook, this is on page 65. Now, before you stop watching this video and you just say, oh, I can read the example and figure it out, don't do that, okay? We are going to tackle this example very differently than what the textbook is giving us. The textbook really doesn't populate a phase diagram actually at all in this example. They just use a bunch of the derived equations, which is what I do not want us to do. We are going to solve this problem using the phase diagram approach that we've been talking about so far. And we will see we'll get the same answers that the example 3.1 gives us in the book, but we are going to be doing this the proper way, and this is the way I expect you to do it on your homework assignments. Unless I tell you otherwise, you need to be doing the phase diagram approach. Okay, so in this example, we're given a total volume, we're given a total mass, we're given a moisture content, you see that here, and we're given a specific gravity of soil solids. And we're being asked to compute total density, that's rho, dry density, void ratio, porosity, and degree of saturation as a percentage, okay? So under solution, here's what I want to first note. I want us to first note that do we need to assume any values here? The answer is no. So first note that we do not need to assume any values, okay? Why is that? Well, notice that we are given two non-ratio values, right? So we don't need to assume anything is equal to 1 because we are given two values that are not ratios, right? What are they? Well, we're given a total volume here. That's not a ratio. And we're given a total mass here, which is also not a ratio. Really, we only need one non-ratio value, but we're given two. So we don't need to assume anything. So that's great. The next thing we need to do is say begin by drawing a generic phase diagram, okay? So that's how we're going to tackle all of our problems. All right, so let's draw this generic phase diagram. Of course, we have air, water, and soil. And let's make the left side, let's go ahead and just make that mass in kilograms. And it really doesn't matter what side is mass and what side is volume. We'll make the right side volume in meters cubed. Okay, so let's go ahead and populate this. So on the mass side, we have a mass of water and a mass of soil solids. And we also have this total mass here. Okay, and on the right side, on the volume side, of course, we know we have a volume of air, we have a volume of water, and we have a volume of solids, and then the air and the water together make up a volume of what? Volume of voids, and then all three volumes together make up the total volume. So let's go ahead and populate what we know. Well, if you notice, we were given two values, a total volume and a total mass. So I'm going to go ahead and write those in there, okay? I'm going to say my total volume is equal to 7.08 times 10 to the minus 3. And if you write your units up at the top label for mass and volume, then you don't need to write the units everywhere inside the phase diagram, okay? And on the total mass side, we're given 13.95 kilograms, okay? So we've gotten two of those initial, those values given to us. We don't need to assume anything. So how do we relate volume and mass? Well, we relate volume and mass through density, okay? So let's make a note of that in case we don't remember. We're going to relate volume and mass by density values, okay? So let's go ahead and see what we can come up with. So let's first start with saying specific gravity of soil solids is the density of soil solids divided by the density of water, okay? Now, what is my density of soil solids? Well, how about we say density of soil solids is, let me erase that. How about we say density of soil solids, make an arrow here, is equal to specific gravity of soil solids times the unit weight, the density of water, okay? Now, were we given G sub S? Absolutely, right? We were given G sub S as 2.66. G sub S is unitless, right? Specific gravity is unitless. So let's punch this in. We get 2.66. What is the density of water? Well, it's not 9.81 kilonewtons per meter cubed. That's the unit weight of water, okay? You need the density of water, right? So the density of water is going to be 1 megagram per meter cubed, or 1,000 kilograms per meter cubed. But we're going to use 1 megagram per meter cubed just so we have fewer zeros in there, okay? So this is going to give us a density of soil solids of 2.66 megagrams per meter cubed, okay? Now, how does this help us? Well, this is where we return to this statement here, relate volume and mass by density. So now that I have the density of soil solids, again, I'm not assuming anything. I'm not assuming rho water is 1, okay? Rho water is 1 megagram per meter cubed. That is something you should remember from fluid mechanics or hydraulics, okay? So here's what we're going to establish. The density of soil solids is mass of soil solids divided by volume of soil solids, right? So we're going to kind of keep this in our back pocket, all right? What about moisture content? We also know the definition of moisture content is mass of water divided by mass of soil solids, okay? Now, do we know moisture content? Yeah, absolutely. We were given moisture content is 9.8%, okay? So what we can say here is 0.098, taken in decimal form, equals mass of water divided by mass of soil solids. And then, of course, we would get the mass of water equals 0.098 times the mass of soil solids, okay? So let's kind of put a little dash box around this. This is, again, we're putting a lot of stuff in our back pocket right now. We'll stick that in our back pocket. What about total mass, right? Were we given total mass? Yeah, absolutely. We already know that. We were given that information, and we already put it in our phase diagram, 13.95 kilograms. Total mass is equal to mass of water plus mass of soil solids, right? So coming down here, we're going to say mass of water plus mass of soil solids equals the total mass, which is 13.95 kilograms, okay? So if I put a little dash box around this, what do we have here? We have two equations with two unknowns, okay? Two equations, two unknowns. So now I can say 0.098 mass of solids plus mass of solids equals 13.95 kilograms, and I get a mass of solids equal to 12.7 kilograms, and I get a mass of water equaling 0.098. That's a 9. Looks kind of like a 7. Let me fix that. 98 times 12.7 kilograms. And so my mass of water should be 1.25 kilograms. So let's go ahead and populate our phase diagram with these two new values, all right? So my mass of soil solids is 12.7. My mass of water is 1.25. So check that out. The entire mass side of my phase diagram is done, right? Is done. So now let's pull these density relations out of our back pocket and go from mass over to volume using definitions of density, okay? So the first thing we can do, since we've already kind of listed out the density of soil solids, how about we work with that first? We could use density of water first too if we wanted to, but let's go ahead and do that. So we can say density of soil solids again is mass of solids divided by volume of solids, and then of course density of water is mass of water over volume of water. So we could start with either of these. We don't have to do either of these in a particular order. So again, I'm just going to start with the soil solids. So I'm going to say my volume of soil solids is equal to my mass of soil solids over the density of soil solids, okay? And my volume of soil solids is equal to, what's my mass of soil solids? Well, I just calculated that. That's that 12.7 kilograms. And what's the density of soil solids? I figured that out earlier, didn't I? 2.66 megagrams per meter cubed, okay? So if I got 2.66 megagrams per meter cubed, watch your units. You need to go 2.660 kilograms per meter cubed, okay? Your units of mass need to match each other, all right? And then we then punch this in our calculator, and we get 4.77 times 10 to the minus 3 meters cubed, okay? And that'll be volume of soil solids. I can populate that on my phase diagram now. Volume of soil solids, 4.77 times 10 to the minus 3. Okay, what about my volume of water? Well, again, I'm going to use my density relationship. Okay, I'm over here now. I'm just going to kind of come make maybe two columns here. So I'm going to have volume of water equals mass of water over density of water. And I'm going to have volume of water equals the mass of water was 1.25 kilograms, and my density of water is 1,000 kilograms per meter cubed, and so my volume of water ends up being 1.25 times 10 to the minus 3 meters cubed, okay? And so then I can populate that on my phase diagram as well. Volume of water is 1.25 times 10 to the minus 3, okay? Now, can I get my volume of air if I wanted to? Yeah, absolutely, absolutely. If I take total volume minus volume of water minus volume of solids, I can also get the volume of air, all right? So, and then I can also very easily get my volume of voids. So let's go ahead and do that real quickly just by punching in some numbers here. We'll say 7.08 times 10 raised to the minus 3 minus 1.25 times, let me try that one more time, minus 1.25 times 10 raised to the minus 3, and then minus 4.77 times 10 raised to the minus 3. So I get a volume of air equals 1.06 times 10 to the minus 3. Yep. And then my volume of voids would be the sum of my volume of air and volume of water. So let's add that to the volume of water plus 1.25 times 10 raised to the minus 3. So my volume of voids comes out to be 2.31 times 10 to the minus 3. So that's it. Our phase diagram is finished. Now we are ready to calculate all of the final values that we were interested in. All right, so now we can say, now my total density is total mass over total volume. Could I have calculated this at the very beginning of this problem? Yeah, sure. You were actually given both of these values at the onset of the problem, but we said we need to compute and populate this phase diagram first. So when I make this computation, I get 1970 kilograms per meter cubed. That's one of my answers. Dry density. I end up with mass of solids over total volume. So my mass of soil solids, let's scroll back up to our phase diagram and see what that was. Actually, there it is right there, 12.7 kilograms. 12.7 kilograms divided by 7.08 times 10 to the minus 3 meters cubed. And let's see what we get. 12.7 divided by 7.08 times 10 raised to the minus 3. And we get 1794 kilograms per meter cubed. Okay, what else did we need? We needed void ratio. What is void ratio? So that is volume of voids divided by what? Volume of solids. You need to make sure you know that. So volume of voids, we calculated that earlier. Let's go to the phase diagram. Here it is, 2.31 times 10 to the minus 3 over 4.77 times 10 to the minus 3, so 2.31 divided by 4.77. So I get 0.484. 484, and that's unitless, right? What about porosity? That's volume of voids over total volume, right? So my volume of voids is 2.31 times 10 to the minus 3 divided by total volume. So that's 7.08 times 10 to the minus 3. Of course, the 10 to the minus 3's cancel. So you could just take the coefficients without the 10 to the minus 3 in the numerator and the denominator. But I get 0.326 as my porosity. And then we need the degree of saturation. So what is the definition of the degree of saturation? That is the volume of water divided by the volume of voids. Again, it's how much of the void space is filled with water. And so we can look at our phase diagram. We have all the numbers there. We say volume of water divided by volume of voids. And we get about 0.54, but the problem did state we want it as a percentage. So maybe we should put in 100% here. Okay. And so when we type this in, punch this through, we get 54.1%. And that's it. So if you notice that these are the same values that are summarized in the example. The example did not use a phase diagram, but you must use a phase diagram. If you are not using a phase diagram, you're going to lose a lot of points. So use the phase diagrams, fully populate them, then just use these basic definitions. For now, I do not want you to use the pre-derived equations to solve for these values. Use the basic ratio definitions.